Just to make the last idea concrete, and the lower bound matches the upper bound for a 5-element sorting network. Imagine we have 4 elements we want to sort. There's 24 factorial permutations that we somehow have to each put in its own little box. Again, the algorithm has to, successfully distinguish between each of the 24 factorial permutations. Now, I'm not saying that this is the way a particular sorting algorithm works, but the best possible thing for it to do would be to split it as evenly as possible, and think about why I have to split evenly as possible in a moment. So 24 we split evenly as possible, we get 12 and 12. So this splits the 24 possible things into 2 sets of 12. Then, if we're lucky, we get another sorting thing that's going to split the number of compatible permutations into 6, 6, and 6, and 3, 3, and 3. Finally here, when we get 3, well, when we split, we will find out one thing, but there still will be 2 consistent things over here. And eventually, finally, we have to split this 2 case, and this required 5 comparisons. So, what's the minimum binary tree that you can have on that has to have n factorial things on the bottom? What's the one that's supposed to even on top? Yeah, so that's, and here we see that the lower bound matches the upper bound. So let's see how first try to evolve things. Okay. We can express a sorting network as a sequence of comparisons. We discussed that before. Hillis designed an encoding, which would find sorting networks of size 60 to 120. So unfortunately, he didn't have a chance of beating the record. It might have been when he first did it that the record of 60 wasn't known at that time, but he aimed to try to get close to it. Okay. So we'll go into the encoding in a moment, but one thing which Hillis did, which is kind of an interesting idea. So one thing you notice about this encoding is its variable length. It's not a fixed length encoding. It's going to somehow encode, well, it is a fixed length encoding, but it's going to encode for something from 60 to 120 comparisons. And the basic idea is that if you have an allele which is homozygous, i.e. they both code for the same thing, or they both code for one comparison, then that allele corresponds to one comparison. If you have the 2 chromosomes and one thing expresses one on the top and one expresses on the bottom, then it's going to be 2 comparisons. We'll see this when we look at a picture of how it works. Okay. So the idea, what happened?
What do you have to focus?
Just out of focus. Mysterious. Okay. The fact that things are in binary is kind of a detail. Let's not worry about the fact that they're in binary. You have 4 bits. You can encode a number between 0 and 15, or a number between 1 and 16, depending how you're thinking about it. So our sequence of comparisons looks like, here's a comparison between 11 and 5, here's a comparison between 7 and 9, 14 and 4, and so forth. But just like in people, something different than the other GAs we're using is the genetic information is going to come in paired strands. So this is 15, this is 1 plus 2 plus 8, this is 11 in binary, this is 11 in binary. these are both coding for 11. These are both coding for 5. This expresses the comparison 11.5. Whereas now in this, you notice things don't match up anymore. So the first comparison 7, 9. This is 7 and 9, and then the bottom thing is 2 and 7. So they no longer match up. So you can have things which are homozygous or heterozygous, where a given location, either you have the comparison encoded once, or you potentially have it encoded twice, because you can have this double bit string representation. Okay. So the top string encodes 7, 9. The bottom string encodes 2, 7. So we have 2 comparisons here. They both encode 1. So if we have a total of 60 pairs, if everything is all the same, we encode 60 comparisons. If in these 60 pairs nothing matches up at all between pairs, we have 120 comparisons. Questions about how that representation works? So we have 60 pairs of numbers. Okay. Okay, so the experiment started out as follows. Fitness was calculated on a random sample of test cases. You could calculate, yes, you could check all possible permutations or some subset of them, but some random sample of test cases corresponding to how calculated fitness. And the fitness was just the percentage of cases that the algorithm sorted correctly, or that the given chromosome, which corresponded to these 60 to 120 comparisons, sorted correctly. The GP, the genetic algorithm, because of some details, it doesn't look like a standard GA. The way, and there's many things one can try. Instead of doing fitness proportional selection, essentially the bottom half of the population was deleted, and each member of the top half created one offspring. Okay. And I'm leaving out some details here. This is approximation. Furthermore, if you remember these techniques which people use to slow down the change of things, individuals were placed on a 2D grid where mating occurred locally. Okay, so we mentioned this idea of rather than having everything in a pool, we had things on a 2D grid. I asked you to speculate why the speciation. Well, we discussed one reason. There's another reason you probably won't get unless you know who Danny Hillis was at this time, what his job role was. Past computer science. So this was a time for a while, and now it's certainly come back, where there's going to be a parallel revolution. And one of the companies that was going to lead the parallel revolution was the Connection Machine Company, and Danny Hillis was like the chief research scientist there. And so this program was a demo for what you could do on their parallel connection machine, and so it was some sort of hypergrid of processors in the 80s, and so it's natural to have computation spread out over a grid anyway, since you could simulate a grid with the hypercube, and so there was a computational reason to have this setup, besides the normal setup for speciation. Okay. So crossover is more directly, since we have a diploid representation, unlike the usual GA where we don't have a diploid representation. So crossover works like it for this works like it did in people. Crossover, each parent created a gamete, and then the gametes from each of the parents were combined. This happens for each of the 15 sets of chromosomes. Okay. So this is where an interesting idea comes in. So recall the way the fitness of a given individual was measured was only in the percentage of test cases that sorted correctly. So in the fitness function, there was nothing that said, oh, I prefer a shorter network to a longer network. Okay? So fitness only depends on the size of the, only on the correctness, not on the size. Yet, when Hillis ran this, there was an evolutionary pressure to evolve shorter networks. Why should this system, to the degree which I've specified it, tend to have a preference for shorter networks than longer networks? Observe that if you have something that's correct for 60 comparisons or 72 comparisons so far, you can always add on another comparison at the end, and it doesn't reduce its fitness because another comparison compares, and adding on an extra comparison never hurts the fitness. So why should we tend to evolve short representations in this diploid setup? Ideas. Why short? Why short? If you don't want to answer why short, if something so far is unclear, please ask me to clarify. Yes, please.
Perhaps because shorter networks are generally easier to deal with computationally. And if by adding, say, an extra pair doesn't hurt the fitness, you could argue, well, it does not necessarily, I'm probably generalizing this too much, it will not necessarily, if you prefer found, or if you agree. Just cut off the last bit of what I said and just go for computational complexity.
Well, I mean, in the sense the computational complexity isn't measured in the fitness, so it doesn't make a difference relative to this evolutionary setup. So we're looking for a different explanation.
Easy to visualize?
Easy to visualize. No. Yes.
Only the top 50% of the networks survive. So that means the shorter networks, the surviving ones, will tend to be the more efficient ones or more fit ones because they have more room to explore from there. If all of the networks that survive already have 120 comparisons, it's difficult to have offspring. Whereas if you have two that just have 60 comparisons, you could just put those two in a row and basically do the sorting twice, and we'll probably achieve a higher fitness.
It's possible. I kind of got the flavor of what you said. I haven't thought it through, so I neither want to say that what you said is correct or incorrect. It may be that you've caught on to some other explanation, but it doesn't happen to be the exclamation box that I'm looking for. But I'm interested in hearing ideas, and that seemed like, I didn't understand all the details, but it seemed like a flavor of.
The
Yes.
smaller size of the network allows more combinations.
I think that's kind of similar to his idea, and I don't, but maybe it's different, but smaller network allows more combinations. I don't see the necessary connection between that and fitness. Yes?
Because fitness is based on the correctness. When it's short, you make less mistakes.
Well, I mean, I don't exactly agree, because any short network, you can have any extension after it, and it won't change the fitness. If it's correct in the first 65 comparisons, whatever you throw on after that, it'll remain correct, because it never changes something that's in a correct position already. Yes, and then I'll offer a typical explanation, but maybe there's
there are coding regions, and usually they give some information as in exons in a DNA, so they are usually smaller. So if you consider a smaller sequence, you might get more out of a sequence.
don't understand the details.
Okay.
But it's going to be related to what we're going to talk to GP, because we're going to make a connection between this and a similar thing in genetic programming in a little bit. Final.
Ron wants to try too. Haven't you just told us pretty much the answer? I mean, you said if you say got 70 of them and you've already found it effectively.
Yes.
Adding more does not necessarily improve or harm fitness.
Right.
So, in effect, those extra ones are superfluous to requirements.
Yes.
So, is that not?
But why? So if they're superfluous, there's no reason to select those or shorter one. And in fact, there's probably many more longer ones than there are shorter ones that sort correctly, and they're going to have the same fitness.
Yes, but in that case, you would prefer the I see what you mean.
Personally, we would prefer it, but the fitness function doesn't know. But you're on the right track. I don't know if you want to answer. You want to answer? Otherwise,
Is it robustness? Is it that longer ones are more susceptible to mutation or having their code?
Yes. I'm sorry. Yes, I'm going to grow your. It is some form of robustness, and we'll make this precise in a different scenario with genetic programming, but it's an idea of effective fitness. Now, suppose we have two sorting networks. They're each correct. Okay. And in fact, the difference between the sorting networks is, maybe one's longer, but they're both correct up to some point. But the other one in its diploid representation is less efficient, i.e., instead of having some comparison twice, it has a different comparison. Okay? That maybe comes later on, one of the comparisons is unnecessary. This 2-4 is unnecessary, but we really need the 3-4. So this network maybe ends up being longer by one comparison effectively, or something of this nature. So they're equally as fit. This one is slightly longer. But rather than thinking about the kind of direct fitness, think about the fitness into the second generation. This network, having 3-4 twice, is more likely to survive crossover or mutation, i.e. that crucial comparison will still be there. Okay? Whereas this where it has only 3, 4 once, it may lose that crucial comparison in the next generation. So things that have these important comparisons twice are more likely, that comparison is more likely to survive unto their offspring. So if we look at fitness relativized to the offspring's offspring, the offspring's offspring of this will be more likely have a higher fitness than this, and so things like this tend to survive more. Looking to generation.
But did you say it's because it had 3, 4 twice? I didn't get what you meant.
Okay, so we have a diploid representation. So the idea, sorry, I should do, so here maybe we have one sorting network that does 1, 2, 3, 4, 1, 3, okay? Remember, things are diploid, so maybe the way it represents, we end up with, everything is duplicated. But we have another network that instead does 1, 2, 3, 4, 1, 3. I'm not saying that these are sorting networks. And then it does 1, 2, and then it does 1, 4, and then it does whatever, 2, 3. So this has all the. Let's say this is the critical sequence, okay? I'm waving my hands about why this should be the critical sequence, but this has a critical sequence and it has it twice, because we have this diploid representation, whereas this is representing a slightly longer sorting network, 1, 2, 3, 4, 1, 4, 1, 3, 2, 3. It sorts just as correctly because it has these 3 things, but what? But if we look at this person's offspring, if there's some, an offspring is more likely to have each of these since it occurs twice, whereas the offspring here, not all of them are occurring twice, so it's less likely an offspring to have it. So if we get a population dominated by these, bad things are less likely to destroy an individual position, whereas there's a mix in the population, you're more likely to destroy the crucial comparison. And we'll make this notion of effective fitness in a little more exact in a different context of genetic programming. Okay. So this in itself is an interesting thing, independent of coevolution. I didn't write down the number. I can't remember, but Hillis ran his program. He got some value. I think maybe it was 63 comparisons at this point. I can't remember. So then Hillis had this idea that, let's try predator-prey coevolution. So Hillis hypothesized why evolution wasn't working well is, since he wasn't trying all test cases, but he was trying some random sample of test cases, that the test cases weren't challenging enough. I.e., the network found a good strategy for the test cases randomly, but really should have more challenging test cases. Okay? And so the idea of what Hillis did is test cases were then modeled as parasites. Okay? And we'd have 2 things evolving. So a test case was some 10 to 20 comparisons to try in the sorting network. Each spatial location now contained a test case and a sorting network. Okay? The fitness of the network would be the percentage of correctly sorted test case examples. Okay? The fitness of the test cases were the number of test cases that fooled the network. Okay? Under this new model, it improved from, I think, 63 comparisons to 61 comparisons as a result of a number of runs. So Hillis found this advantage of predator-prey coevolution, which was quite influence, show the use for it. Questions? How this works. The idea is fitness would be determined by a set of test cases. So the fitness of a sorting network was the number of test cases it got right. We also, at the same time, what was evolving were a bunch of test cases. The fitness of a set of test cases was how good it was at fooling the sorting network. So, you sum the two percentages and they sum to 100%. Okay, questions? Okay. If we get to it, I'm going to go ahead and do genetic programming next, but this is another kind of classic GA thing which I hope to get to today. Learning in the Baldwin effect, how learning can guide evolution. And I didn't find out if Hinton did this while he was at UCL, but Hinton was one of the founding members of Gatsby. So this is Gatsby's contribution to genetic algorithms. A contribution. Okay. Let's go ahead and start thinking about GP, and then we'll come back to that because I want to give you the background for your homework. Okay. Before we talk explicitly about GP, I want to show you. I should really do a demo, but because I like putting slides of paper on visualizers rather than pulling out computers, I'm going to just continue to put slides of paper on visualizers because it's a simulated demo. It's a demo of a demo. There's a lot of programs like this. A lot of people like this idea of using evolutionary computation to create art, and there's books on this. Peter Bentley certainly written about it. There's a lot of people who try to use evolutionary computation to create art, and this is a real toy example, but it's going to demonstrate some nice examples for genetic programming. So the idea of using evolutionary computation in art usually works as follows: is you, the artist, you get to make some choices. Like somehow the system puts up some images, and then the fitness function is you. You go, oh, that's pretty, that's pretty, that's pretty. And then somehow it combines those images together, or maybe there's more things, and you get the next generation. You continue to get the pretty picture that you want. I'm worried that I have these out of order, but whatever. It's not, I'm doing Peter Cornelius, I'm doing, I forgot, Jan van Hennert, a bad job. But here's an example of a little Java demo that I found on the web. So it generates some of these pictures in the style of Mondrian, for those who are familiar with Mondrian. And you then select images that you think are kind of interesting to you. So I select this image, that image, and that image. The idea is that in the next generation is that it should somehow do GP on it. It should choose images that are like the ones you've chosen and maybe combine in some way. So after that, I got, not surprising, I chose a yellow block. I got some more yellow blocks. I got some more red blocks. I generally got some simpler things. So I kind of chose the simpler things before. I did it again. And in addition to, I really like that plain yellow block. I thought, this is kind of cool. This is kind of like a weird American flag. I'm bringing American flag. My flag. Sorry for those of you who love flags. Then I got this, and so forth. I'm not going to detail, I may not be the greatest artist in the world or the greatest GA artist, but I'm sure you guys love my hand drawings. But anyway, why am I telling you all about this program? Well, what was the story in the first part of the course? The first part of the course, this is still the first part of the course, but this idea of universal Darwinism, where we build some evolutionary computation algorithm, the key idea to our evolutionary algorithm was kind of abstract the operators and applying them in new situations. So we needed some form of selection. So in this setup, it's clear that I'm the selector, okay? But the other part of the story is we need some representation for things which were evolving, and we perhaps need some equivalency of the mutation and crossover operator. But before I even get to the mutation crossover operator, looking at these pictures, what do you think the representation is? Before somebody shouts out the answer, why don't you take a minute to imagine, well, if you were evolving these Mondrian paintings, what could you use as a representation? You could have quite complicated ones, like on this page. Very complicated. But since I'm going to do an example, I'm going to stick to an easy one. Complicated equilibrium problem. Unless you have a question. Do you have a question or answer?
No, kind of answer.
Okay. Well, why not? How might you do this?
I was going to say split it up into sections and just say lines in each section, like kind of borders. So you just have squares, split into sub-squares, and then you would have a border around each square that you decide to highlight, say.
So you can imagine you have some grid and you decide whether the squares are in the given color or not. Certainly a possible representation. There's a lot of regularity in these which suggests that it's doing something slightly different. See if you can guess what. So that was a good guess, and it's certainly an alternative representation one could use for evolving images. But what is the representation that this person's using? Thought I brought my colored markers. Yes.
Looking at the elements of variation, the sizes differ somewhat, so you'd consider that to be an element, perhaps in a sort of array, and then the number of elements that you have, the number of squares or rectangles within the space, and then the number of each specific color. So something like that it could be used in a vector.
I don't know all the details, but it's not going to be a vectorial representation or a matrix representation. Yes.
A tree, maybe.
Oh, yes. Now let's see how it works. I normally do this with colored pens.
I think your coloured pen's on that seat under there.
Thank you.
I think so.
Yes, we have color. Okay. Which one of these should I do? I think so. I need a blue. I need orange to substitute for yellow. I need a red. A little bit black. Okay. Let's do this one. It's not so complicated. Actually, I'll use white as orange. Let's do that one instead. Okay. Yeah, the choice is arbitrary to the artist, but this is what the artist happened to do, and okay, it sets up this lecture, so I chose it. Actually, these are the same. Let's do this one. Okay, so the idea is we're going to use a tree structure, and there's a little bit of distortion, but the basic idea is we tree-like split the image. So the first split that's a split in the middle, and it's a horizontal split. So we write down our horizontal split. We have to then determine what happens on both halves. So something happens to the right, something happens to the left. What happens on the right is just a red blob. So we can end that in the terminal, which will be the terminal red. Okay. Then what happens next? It seems like we have another horizontal split. So then we go ahead and we write H. And we have this, the splits are always in the middle. So we have this horizontal split. What happens to the right? Well, what happens to the right is just the color white, which is going to be represented as the color orange. Then what happens to the left? We get a vertical split.
Isn't it the opposite? Is it vertical?
No, horizontal was the first, right? That's in the middle. Then the next split that's happening.
I mean, the first one that separates both halves, that's vertical, right?
Ah, yes, I'm screwing up. Horizontal, vertical. Vertical. I know there's a reason my wife doesn't like this. Okay, so here we go. We have the two vertical splits. Now we have a horizontal split. Thank you for pointing out the difference. Horizontal split. Well, left is always left. Up will be left. So up will end up being turned into a blue, and then the right will end up being turned into another vertical split. Then that vertical split gets turned into a blue. This is starting to get long. Then we have another horizontal split, and that horizontal split gets turned into white. And oh no, I said that should be red actually, because I said up is left. Red. Sorry. White, green, white. Okay, so this is our tree-like representation, and this is the story that I used. And so, okay, so we have a way of representing drawings. Great. But it's kind of nice because we've done permutations, we've done bit strings, and now we're going to have genetic programming. There's many possible representations, but certainly the first representation that really caught on was representing code or types of code through expression trees, and so people who are familiar with Lisp-like or scheme-like languages are perhaps used to thinking of code being structured like a tree. And so the idea is now, instead of evolving a bit string or a permutation, we're going to evolve some tree-structured code. Okay. Questions so far? I always lose everything. Can somebody tell me the time if we should have a break now?
It's 4 o'clock.
What?
It's 4 o'clock now.
4 o'clock now. Maybe it's sensible because it's right at the start. Let's go ahead and break and then return to genetic programming.